Hello, I'm Antonio Paolillo from the Huawei Dresden Research Center, and today I'll be talking about our CLoF framework, a framework to compose logs for multi-level NUMA systems. Nowadays, concurrent software is everywhere. Databases, operating systems, and applications all make use of concurrency to achieve good performance. One of the most prevalent concurrency mechanisms is the spin lock. Logs used to be just 2 or 3 operations plus one compare and swap. But as the hardware evolved and more cores have been introduced, logs have become much more complex, with hundreds of lines of code and several atomic operations. They have to be fast and avoid starvation and minimize contention. Otherwise, the concurrent software would not scale. They are also quite difficult to get right, and current hardware trends worsen the situations. There is a variety of hardware configurations, architectural details, and memory models that make it hard to develop a one-size-fits-all locking algorithm. We'll now take a look into the safety and scalability challenges we faced when designing logs for modern hardware. Large server machines have non-uniform latencies when accessing different segments of the memory. When threads run on cores near to each other, their communication is fast. When they run on distant cores, their communication is slower. This forms a hierarchy of memory accesses, depending on the position of the threads. We used one of such large servers, a x86 machine with 96 CPUs. This heat map is obtained when 2 threads share an atomic counter, and the threads are scheduled on all possible pairs of CPUs. Tiles are darker when the thread performance is better. We see that the performance is very much affected by the position of the threads. We can distinguish several levels. As shown by the secondary diagonals, when the threads are executing on 2 hyperthreads of the same core, the performance is very good, as it maximizes locality. Then the small squares of 3 CPUs represent cores sharing a L3 cache partition. The performance is still very good. There is a faint group of 24 threads. These are the CPUs that are located in the same NUMA node. The lighter squares correspond to the throughput achieved when the threads are on different packages. Proper use of the full hierarchy is important for scalability. For example, HMCS is a log that can understand the hierarchy and exploit it. HMCS 2 and 3 only use partial knowledge of the hierarchy, while HMCS 4, a configuration we derived for this machine from looking at the heat map, has a complete view of the hierarchy. A benchmark shows that it is by far the best version once the contention increases. Although it has not been published previously, it outperforms the original HMCS 3 by up to 60%. We think that encoding the full hierarchy in a multi-level log has a great potential to improve its performance, because it enforces some form of locality when passing the log. Notice that the hierarchy will look differently on different machines. As we can see here on our ARM server, this one has no hyperthreading and bigger differences when crossing NUMA nodes and packages. The story is not over. We also notice other differences. Different logs also perform differently according to placement. For example, take these 3 classic logs: ticket, MCS, and CLH. When crossing the package, ticket outperforms the other, while inside the same package, MCS seems to be the best and ticket lot performs poorly. We also observe different performance of logs when comparing platforms. On the right is the same experiment, but on the ARM server. In the same package, the best log is CLH. On x86, the best is MCS. We can exploit these observations to opt to further improve logs performance. Our approach, which combines multi-level with heterogeneity, yield even better gains than the best HMCS configuration. The previous observations make us envision a hierarchical log that supports several NUMA levels, with each level employed a different sub-algorithm. Showing that such a log is correct can be very challenging, especially since we want to support architectures with different memory models. In contrast to the TSO model implemented in x86, the weak memory model, implemented in ARMv8, allows it to aggressively reorder the memory accesses to optimize performance. But often in concurrent code, the order of operations is critical. To avoid these memory reorderings and ensure correctness, one has to carefully place barriers in the concurrent code. One single missing barrier can cause a concurrent system to hang, crash, or corrupt data. Too many barriers can hamper its performance. Traditional testing techniques cannot ensure the barrier placement is correct, not even of simple logs implementation. Luckily, state-of-the-art model checkers, such as GenMC, can verify that, without relying on full-fledged formal proofs. Unluckily, no existing model checker is capable of verifying that for a complete hierarchical lock in a reasonable time. For example, we tried to verify HMCS4 with GenMC, but it didn't finish within a day. So how can we advance the state-of-the-art of locks? We want to support heterogeneity, deep and arbitrary NUMA hierarchies, and at the same time, we want to be confident that our concurrent system will not crash nor hang. For that, we propose a framework that addresses all these challenges. CLoF composes locks in an arbitrary multi-level hierarchy. In each level, CLoF can use a different lock implementation, for example, ticket or MCS. And the composition of these locks is correct by construction on weak memory models. No prior work has tackled all these challenges at the same time. Most papers do not even mention barriers for weak memory models. As presented in their papers, CNA and shuffle lock would not work on ARM. HMCS does mention barriers for weak memory models, but unfortunately these are insufficient, causing the lock to hang on ARM. Among prior work, only the lock cohorting technique supports heterogeneity. However, its hierarchy is limited to 2 levels, as most NUMA-aware locks. In contrast, HMCS supports arbitrary hierarchies of MCS locks. This is how CLoF is used. Using the heat map presented previously, we define the hierarchy suiting the target platform. We pick a set of basic locks that are not NUMA-aware. These are verified and optimized for weak memory models with vsync, a tool we developed in a prior work. According to the specified hierarchy, the CLoF lock generator is then able to compose these basic locks into multi-level locks that are correct by construction. Hundreds of such combinations can be created. We evaluate them all in a scripted benchmark. Finally, we select the best performing combination for the target platform. How do we build a hierarchical lock? For that, let's consider a system with 2 NUMA nodes and a few threads. When a basic lock, call it L0, protects a critical section, many threads access this lock, causing the data to frequently bounce across NUMA nodes, slowing the performance down. To avoid that, we add 1 lock per NUMA node. Threads first have to acquire the lock of their NUMA node, L1 or L2, before acquiring L0. We call a CLoF lock a composition of a low-level lock with a high-level lock, for example, L1 with L0. Assume a thread acquires L1 then L0, and is currently in its critical section. Once it wants to leave the critical section, it has 2 options. Either it releases L0 and then L1, allowing threads of the other NUMA node to acquire L0 and enter the critical section, or it releases only L1 and passes L0 to the next owner of L1. In this way, keeping the critical section in the same NUMA node. After some time, threads are forced to release L0 to avoid starvation of the other NUMA node. If we split the NUMA nodes further into multiple cache groups, then we can define a CLoF lock recursively, for example, L3 with big L1. In this way, we support multi-level hierarchies. Each of these levels can have a different basic lock implementation, and with that, we support heterogeneity. As mentioned before, on weak memory models, model checkers cannot verify the whole tree with many levels and different lock implementations. That would take too long. Instead, to make this verification possible, we divide and conquer, combining an inductive argument with model checking. We first verify that the basic locks are correct with the GenMC model checker. This is our base step. And for our inductive step, we verify the CLoF combination of 2 abstract locks. Such a small hierarchy can be easily verified with GenMC in less than 10 seconds. Now, it follows inductively that any combination of basic locks with any number of levels is correct on weak memory models. With the CLoF lock generator in hand, we can now safely generate any lock combination. The scripted benchmark generates and evaluates all of them. We show here the results on both our platforms in a hierarchy with 4 levels. With 4 basic locks, there are 256 combinations. We rank all combinations, balancing their performance trade-off at different contention level. This selection policy picks the best and worst lock among them. As a baseline, we use HMCS4 configured with the same hierarchy. Observe that on both platforms, the best CLoF locks outperform HMCS. Also observe that on different platforms, the best CLoF locks are different. They are composed of different basic locks. Of course, in the paper, we provide a more detailed analysis. To conclude, Efficient NUMA-aware locks must be tailored to target multi-level NUMA systems. CLoF fully leverages the deep NUMA hierarchy and the level heterogeneity by composing basic locks into many NUMA-aware locks. These basic locks can be verified on weak memory models with a model checker, and inductively, the generated locks are correct by construction. A scripted benchmark selects the best performing CLoF lock for the target system. The best CLoF lock greatly outperforms state-of-the-art NUMA-aware locks. Running on both ARM and x86, CLoF yields twice the throughput of CNA lock and shuffle lock in multiple benchmarks. In our paper, we cover many more details. Among other cool things, we explore tuning points, platform-specific optimizations, and analyze the best CLoF lock combinations. As future work, we would like to consider implementing CLoF in the Linux kernel, and maybe big little platforms, for even more fun with more heterogeneity. Thank you very much for your attention, and let's meet in Q&A.